This is how intelligence is made. A new kind of factory. Generator of tokens. The building blocks of AI. Tokens have opened a new frontier, turning data into knowledge and drawing on all we have learned. Tokens are harnessing a new wave of clean energy. And unlocking the secrets of the stars. In virtual worlds, they help robots learn. And in the physical world, perfect. Forging new paths. And clearing the way for a bountiful harvest. In the moments that matter, tokens are already there. And in the miles between, they never stop. They work where human hands cannot. So we may all breathe easier. And the smallest hearts beat stronger. Tokens are helping us break new ground. On a scale never attempted, to empower the world. So we can reach
Star Cloud 1, separation confirmed.
well beyond it. Together, we take the next great leap into a bright new future.
All these people lining up so early in the morning, all of you in here, it's great to see you. GTC. GTC, we're going to talk about technology. We're going to talk about platforms. NVIDIA has 3 platforms. You think that we mostly talk about one of them. It's related to CUDA X. Our systems is another platform, and now we have a new platform called AI Factories. We're going to talk about all of them, and most importantly, we're going to talk about ecosystems. But before I start, let me thank our pre-game show hosts. I thought they did a great job. Sarah Go of Conviction. Alfred Lim, Sequoia Capital, NVIDIA's first venture capitalist. Gavin Baker, NVIDIA's first major institutional investor. These 3 people are deep in technology, deep in what's going on, and of course, they have just a really broad reach of technology ecosystem. Here, 450 companies sponsored this event. I want to thank you. And today, there are probably a cake of artificial intelligence, from land, power, and shell, the infrastructure, to chips, to the platforms, the models, and of course, the most important, and ultimately, what's going to get this industry taken off is all of the applications. When it all began here. This is the 20th anniversary of CUDA. We've been working on CUDA for 20 years. For 20 years, we've been dedicated to this architecture, this revolutionary invention. SIMT, single instruction, multi-threaded, writing scalar code could spawn off into multi-threaded application, much, much easier to program than SIMD. We recently added tiles so that we could help people program tensor cores and the structures of mathematics that are so foundational to artificial intelligence today. Thousands of tools and compilers and frameworks and libraries. In open source, there's a couple of 100,000 public projects. CUDA literally is integrated into every single ecosystem. This chart basically describes 100% of NVIDIA's strategies. You've been watching me talk about this slide from the very beginning. And ultimately, the single hardest thing to achieve is the thing on the bottom, installed base. It has taken us 20 years to now have built up hundreds of millions of GPUs and computing systems around the world that run CUDA. We are in every cloud, we're in every computer. GeForce is NVIDIA's greatest marketing campaign. We attract future customers, starting long before you could afford to pay for it yourself. Your parents paid. Your parents paid. Your parents paid for you to be NVIDIA customers. And every single year, they paid up year after year after year until someday you became an amazing computer scientist and became a proper customer, a proper developer. To explore further and further, 20 years later, 5 years later, the invention of CUDA. One of the biggest investments that we made, and we couldn't afford it at the time, and it consumed the vast majority of our company's profits, was to take CUDA on the backs of GeForce to every single computer. We dedicated ourselves to create this platform because we felt so strongly about its potential, dedication to it, despite the hardships in the beginning, believing in it every single day for 13 generations or for 20 years. We now have CUDA installed everywhere. The pixel shader led to, of course, the revolution of GeForce. And then 10 years ago, we introduced, about 10 years ago, what is it, 8 years ago? We introduced RTX, a complete redesign of our architecture for the modern era of computer graphics, the big bang of AI. 10 years ago, we decided that we would fuse programmable shading and introduce two new ideas. Ray tracing, the world, AI is now going to go back and revolutionize how computer graphics is done all together. Well, today I'm going to show you something about the future. This is our next generation, the fusion of 3D graphics and artificial intelligence. This is DLSS 5. Take a look at it. Is that incredible? Computer graphics comes to life. Now, what do? We fuse of generated worlds. We combine 3D graphics, structured data, the unstructured database, the generative data, Google Cloud, BigQuery. All of these platforms are processing data frames. These data frames are giant spreadsheets, and they hold all of life's information. This is the structured data, the ground truth of business. This is the ground truth of enterprise computing. Well, now we're going to have AI use structured data, and we better accelerate the living daylights out of it. It used to be okay, and we would, of course, we would accelerate structured data so that we could do more, we could do it more cheaply, we could do it more frequently per day, and keep the company running at a much more synchronized way. However, in the future, what's going to happen is these data structures are going to be used by AI, and AI is going to be much, much faster than us. Future agents are going to use structured databases as well. And then, of course, the unstructured database, the generative database. This database represents the vast majority of the world. Vector databases, unstructured data, PDFs. Unfortunately, we can't query it. We can't search for it. It's hard to do that. And the reason for that is because there's no easy indexing of unstructured data. You have to understand it's very into. NVIDIA created two foundational libraries, just like we created RTX for 3D graphics. We created cuDF for data frames, structured data. We created cuVS for vector stores, semantic data, unstructured data, AI data. These two platforms are going to be two of the most important platforms in the future. Super excited to see its adoption throughout the network, this complicated network of the world's data processing systems. And the reason for that is because data processing has been around a long time. And therefore, so many different companies and platforms and services, it has taken us a long time to integrate deeply into this ecosystem. I'm super proud of the work that we're doing here. And then today, we're announcing several of them. IBM, the inventor of SQL, one of the most important domain-specific languages of all time, is accelerating watsonx data with cuDF. Let's take a look at it.
60 years ago, IBM introduced the System 360, the first modern platform for general-purpose computing, launching the computing era. Then SQL, a declarative language to query data without requiring the computer to be instructed step by step. And the data warehouse, each the foundations of
are one of the world's leading storage providers, and they worked with us to create the Dell
at 83% lower cost. The next computing platform has arrived, accelerated computing for the era of AI. Data processing systems can't keep up. Nestle makes thousands of supply chain decisions every day. Their order-to-cash data mart aggregates every supply, order, and delivery event across global operations in 185 countries. On CPUs, Nestle refreshed the data mart a few times a day. With accelerated watsonx.data running on NVIDIA GPUs, Nestle can run the same workload 5 times faster at 83% lower cost. The next computing platform has arrived, accelerated computing for the era of AI.
NVIDIA accelerates data processing in the cloud. We also accelerate data processing on-prem. As you know, Dell is the world-leading computer systems maker, and they also are Google Cloud. And Google Cloud, as you know, we've been working with Google Cloud for a very long time. We accelerate Google's Vertex AI. We now accelerate BigQuery, really important framework and really important platform. And this is an example of our work together with Snapchat, where we reduce their cost cloud. We also accelerate data processing on-prem. As you know, Dell is the world-leading computer systems maker, and they also are one of the world's leading storage providers. And they worked with us to create the Dell AI data platform that integrates cuDF and cuVS to create an accelerated data platform, well, for the era of AI. And this is an example of what they did with NTT Data, huge speed up. This is Google Cloud. And Google Cloud, as you know, we've been working with Google Cloud for a very long time. We accelerate Google's Vertex AI. We now accelerate BigQuery, really important framework and really important platform. And this is an example of our work together with Snapchat, where we reduce their cost of computing by nearly 80%. When you accelerate data processing, when you accelerate computing, you get the benefit of speed, you get the benefit of scale, but most importantly, you also get the benefit of cost. And so all of those come together as one. It was originally called Moore's Law. Moore's Law was about getting performance doubling every couple of years. It's another way of saying, so long as the price remains about the same, and most computers remain about the same, you're also getting twice the performance every year, or you're reducing the cost of computing. We're incredible on PyTorch. We're the only accelerator in the world that's incredible on PyTorch. And incredible on Jackson XLA. And the customers that we support, the Base 10s, the CrowdStrikes, Puma, Salesforce, they're not our customers, but they're customers, developers of ours that we've integrated the NVIDIA technologies into that we can then land on the clouds. Our relationship with cloud service providers are essentially us bringing customers to them. We integrate our libraries, we accelerate workloads, and we land those customers in the clouds. And so, as you can see, most of our cloud service providers love working with us, and they're always asking us to land the next customer on their cloud. And I just want to let you know, there are a lot of customers. We're going to accelerate everybody. And so there'll be lots and lots of customers will be landing in your cloud. Just be patient with us. And so this is Google Cloud. This is AWS. We've been working with AWS a long time. And one of the things I'm super excited about this year is we're going to bring OpenAI to AWS. And so it's going to drive enormous consumption of cloud computing at AWS. It's going to expand the reach, expand the compute of OpenAI. And as you know, they are completely compute constrained. And so AWS, we accelerate EMR, we accelerate everybody in the world. Well, this GTC is really a great demonstration of that. Most of the time you'll see me talk about these verticals, and I'll use some examples. But in every single case, whether it's automotive, by the way, financial services, the largest percentage of attendees at this GTC is from the financial services industry. I know. I'm hoping it's developers, not traders. Guys, here's one thing I wanted to say. And so, in the audience represents NVIDIA's ecosystem upstream of our supply chain and downstream of our supply chain. And we think of our supply chain upstream and downstream. And it's just so exciting that our entire upstream supply chain this last year, irrespective of whether you're a 50-year-old company, we have 70-year-old companies, we have a 150-year-old company who are now part of NVIDIA's supply chain and partnering with us either upstream or downstream. And last year, you had your record year. Did you not? Congratulations. We're on to something here. This is the beginning of something very, very big. And so if you look at accelerated computing, we've now set the computing platform, but in order for us,
Field of science and engineering.
some 70 libraries, maybe 40 models.
20 years ago, we built CUDA, a single architecture for accelerated computing. Today, we've reinvented computing. 1,000 CUDA-X libraries help developers make breakthroughs in every field of science and engineering. cuOpt for decision optimization. cuLitho for computational lithography. cuDSS for direct sparse solvers. cuEquivariance for geometry.
And I couldn't decide what we do. It's going to change how computers are architected, how computers are provided, how computers are going to be a little bit larger. Of course, you could have much larger models than model. O1 was a little bit larger, not much larger, but it's input token usage for context, and it's output token for thinking. Take your context, I can iterate on it, or parts that it could understand. It could ground itself on research. O1 made generative AI trustworthy and grounded on truth. That caused ChatGPT to simply took off. And that was a very, very big moment. The amount of input tokens that was necessary in order to produce and the amount of output tokens it generated in order to reason, the model was a little bit larger. Of course, you could have much larger models than model. O1 was a little bit larger, not much larger, but its input token usage for context and its output token for thinking increased the amount of computation tremendously. Then came Claude Code, the first agentic model. It was able to read files, code, compile it, test it, evaluate it, go back and iterate on it. Claude Code has revolutionized software engineering, as all of you know. 100% of NVIDIA is using a combination of, or oftentimes all three of them, Claude Code, Codex, and Cursor, all over NVIDIA. There's not one software engineer today who is not assisted by one or many AI agents helping them code. Claude Code completely revolutionizes the new inflection. And for the first time, you don't ask AI what, where, when, how. You ask it create, do, build. You ask it to use tools. Take your context, read files. It's able to agentically break down a problem, reason about it, reflect on it. It's able to solve problems and actually perform tasks. An AI that was able to perceive became an AI that could generate. An AI that could generate became an AI that could reason. An AI that could reason now became an AI that can actually do work, very productive work. The amount of computation in the last 2 years, we know that everybody in this room knows the computing demand for NVIDIA GPUs is off the charts. Spot pricing is skyrocketing. You couldn't find a GPU if you tried, and yet, in the meantime, we're shipping GPUs out. Incredible amounts of it, and demand just keeps on going up. There's a reason for that, this fundamental inflection. Finally, AI is able to do productive work, and therefore, the inflection point of inference has arrived. AI now has to think. In order to think, it has to inference. AI now has to do. In order to do, it has to inference. AI has to read. In order to do so, it has to inference. It has to reason. It has to inference. Every part of AI, every time it has to think, it has to reason, it has to do. It has to generate tokens. It has to inference. It's way past training now. It's in the field of inference. So the inference inflection has arrived. At the time when the amount of tokens, the amount of compute necessary, increased by roughly 10,000 times. Now, when I combine these two, the fact that since the last 2 years, the computing demand of the work has gone up by 10,000 times, and the amount of usage has probably gone up by 100 times. People have heard me say, I believe that computing demand has increased by 1 million times in the last 2 years. It is the feeling that we all have. It is the feeling every startup has. It's the feeling that OpenAI has. It's the feeling that Anthropic has. If they could just get more capacity, they could generate more tokens, their revenues would go up, more people could use it, the more advanced, the smarter the AI could become. We are now at that positive flywheel system. We have reached that moment. The inference inflection has arrived. Last year, at this time, I said that where I stood at that moment in time, we saw about $500 billion. We saw $500 billion of very high confidence demand and purchase orders for Blackwell and Rubin through 2026. I said that last year. Now, I don't know if you guys feel the same way, but $500 billion is an enormous amount of revenue. Not one impressed. I know why you're not impressed, because all of you had record years. Well, I'm here to tell you that right now where I stand, a few short months after GTC DC, 1 year after last GTC, at least $1 trillion. Now, does it make any sense? And that's what I'm going to spend the rest of the time talking about. In fact, we are going to be short. I'm certain computing demand will be much higher than that. And there's a reason for that. So the first thing is, we did a lot of work in the last year. Of course, as you know, 2025 was NVIDIA's year of inference. We wanted to make sure that not only were we good at training and post-training, that we were incredibly good at every single phase of AI, so that the investments made in our infrastructure could scale out for as long as they would like to use it. And the useful life of NVIDIA's infrastructure would be long, and therefore the cost would be incredibly low. The longer you could use it, the lower the cost. There's no question in my mind. NVIDIA systems are the lowest cost infrastructure you could get for AI infrastructure in the world. And so the first part was, last year was all about AI for inference, and it drove this inflection point. Simultaneously, we were very pleased last year that Anthropic has come to NVIDIA, that MSL, MetaSL has chosen NVIDIA. And meanwhile, open source models. Open source models have reached near the frontier, and it is literally everywhere. And NVIDIA, as you know, today, we're the only platform in the world today that runs every single domain of AI across every single one of these AI models, in language and biology, in computer graphics, computer vision, in speech, proteins and chemicals, robotics and otherwise, edge or cloud, any language. NVIDIA's architecture is fungible for all of that, and we're incredible for all of that. That allows us to be the lowest cost. We have now proven that. It is the only infrastructure in the world that you could go anywhere in the world and build with complete confidence. You want to put it in any of the clouds, we're delighted by that. You want to put it on-prem, we're happy about that. You want to put it in any country, anywhere, we're delighted to support you. Our computing capability helped us create the kernels, the software that made inference possible. Well, the results all came together, and people used to tell me, but Jensen, inference is so easy. Inference is the ultimate hard. Inference is ultimate hard. It is also ultimate important because it drives your revenues. And so this is the outcome. This is from semi-analysis. This is the largest, most comprehensive sweep of AI inference that has ever been done. And what you see here on the left, on this side, is tokens per watt. Tokens per watt is important because every data center, every single factory, by definition, is power constrained. A 1 gigawatt factory will never become 2. It's physically constrained, the laws of atoms, the laws of physicality. And so that 1 gigawatt of data center, you want to drive the maximum number of tokens, which is the production, the product of that factory. So you want to be on top of that curve as high as you want. The x-axis is the interactivity, the speed of inference, the speed of each inference. The faster you can inference, the faster you could, of course, respond. But very importantly, the faster you can inference, the larger the models, the more context you can process, the more tokens you can think through. This axis is the same as smartness of the AI. And so this is the throughput of the AI. This is the smartness of the AI. Notice, the smarter the AI, the lower your throughput. Makes sense. You're thinking longer. Okay? And so this axis is the speed, and I'm going to come back to this. This is important. This is where I torture all of you. But it's too important. Every CEO in the world, every CEO in the world will study their business from now on in the way I'm about to describe. Because this is your token factory. This is your AI factory. This is your revenues. There's no question about that going forward. And so this is the throughput. This is the intelligence. Better per watt for a given power of data center, the more throughput, the more tokens you can produce. On this side is cost. Notice, NVIDIA is the highest performance in the world. Nobody would be surprised by that. They would be surprised by the fact that in 1 generation, whereas Moore's law would have given us, through transistors, 50%, 2 times, Moore's law would probably give us 1.5 times more performance. You would have expected from Hopper H200, 1.5 times higher. Nobody would have expected 35 times higher. I said last year, at this time, that NVIDIA's Grace Blackwell NVLink 72 was 35 times perf per watt. Nobody believed me. And then semi-analysis came out, and Dylan Patel had a quote. He accused me of sandbagging. He accused me of sandbagging. He says, Jensen sandbagged. It's actually 50 times. And he's not wrong. He's not wrong. And so our cost per token, our cost per token is the lowest in the world. You can't beat it. I've said before, if you have the wrong architecture, even if it's free, it's not cheap enough. And the reason for that is because no matter what happens, you still have to build a gigawatt data center. You still have to build a gigawatt factory. And that gigawatt factory, for 15 years amortized across, that gigawatt factory is about $40 billion. Even when you put nothing on, it's $40 billion in. You better make for darn sure you put the best computer system on that thing so that you can have the best token cost. NVIDIA's token cost is world-class, basically untouchable at the moment. And the reason that's true is because of extreme code design. And so I'm very happy that he named us there was a Monkey King, Token King. Well, we take all of our softwares, and as I told you, we vertically integrate, but we horizontally open. We're vertical integration, horizontal open. We integrate all of our software and all of our technology, however we can package it up and integrate it into the world's inference service providers. And these companies are growing so fast. Our cost 2 times bagged. And that gigawatt factory, for 15 years amortized across, that gigawatt factory is about $40 billion. Even when you put nothing on, it's $40 billion in. You better make for darn sure that he named us. Well, we take all of our softwares, and as I told you, we vertically integrate, but we horizontally open. We're vertical integration, horizontal so fast. Everybody's looking for land, power, and shell. Once you build it, you bring to bear about 700 tokens per second. Average went to nearly 5,000, 7 times higher. And so this is the incredible power of extreme co-design. I mentioned earlier the importance of factories. This is the importance of factory. Your data center, it used to be a data center for files. It's now a factory to generate tokens. Your factory is limited no matter what. Everybody's looking for land, power, and shell. Once you build it, you are power limited. Within that power limited infrastructure,
16 GPUs connected with full all-to-all bandwidth. On April 6, 2016, a decade ago, we introduced DGX-1, the world's first computer designed for deep learning. 8 Pascal GPUs connected with the first generation NVLink, 170 teraflops in one computer, the world's first computer designed for AI researchers. With Volta, we introduced NVLink Switch, 16 GPUs connected with full all-to-all bandwidth, operating as one giant GPU. A giant step forward, but model sizes continued to grow. The data center needed to become a single unit of computing, so Mellanox joined NVIDIA. Chips.
Unstructured data, cuVF. When we think Vera Rubin, we think the entire system. Vertically integrated, completely with software. Extended end-to-end. Data center CPU in the world that uses LPDDR5 generation scale-up switching system. This is not Ethernet. This is not InfiniBand. This is already, for sure, going to be a multi-billion-dollar business for us. So I'm very, very pleased with our CPU architects. We designed a revolutionary CPU. And this is the CX9 powered with Vera CPU, the Bluefield 4 STX, our new storage platform. Okay, so these are the racks, and it's connected. Each one of these racks, the NVLink rack, this is, I've shown you guys this before, it's a super heavy. It seems to get heavier every year, because I think there's just more cables in there every year. And so this is the NVLink rack. We've also taken this technology, because it is so efficient to create a data center with these cabling systems, structured cables. So we decided to do that for Ethernet. So this is Ethernet 256 liquid-cooled nodes in one rack, and it is also connected with these incredible connectors. You guys want to see Rubin Ultra? So this is the Rubin Ultra compute node. Unlike Rubin that slides in horizontally, Rubin Ultra goes into a whole new rack. It's called Kyber, that enables us to connect 144 GPUs in one NVLink domain. And so the Kyber rack, this, I could lift it, I'm sure, but I won't. It's quite heavy. This is one compute node, and it slides into the Kyber rack vertically. This is where it connects into. This is the midplane. The Kyber racks, and each one of these racks is a different compute node, and this is the amazing part. This is the midplane, and the back of the midplane, instead of the cabling system, which has its limits in terms of how far we could drive cables, copper cables, we now have this system to connect 144 GPUs. This is the new NVLink. This sits also vertically, and it connects into the midplanes on the back. Compute in the front, NVLink switches in the back, one giant computer. Okay? So this is what happens when you don't practice. Okay, all right, so take your time, just don't get hurt. You saw this slide. You know, only on NVIDIA's Keynote will you see last year's slide presented again. And the reason for that is I just want to let you know that last year I told you something very, very important. And it's so important, it's worthwhile to tell you again. This is probably the single most important chart for the future of AI factories. And every CEO in the world will be tracking it, will be studying it very deeply. Grow from maybe 100,000 tokens, input length, axes. On the vertical axis, thank you guys. On the vertical axis is throughput. On the horizontal axis is token rate. Today, I'm going to show you this. Because we're now able to increase the token speed, and because model sizes are increasing, because the token length, the context length, depending on the different grades of different application use case, continues to grow from maybe 100,000 tokens input length to maybe millions. The token input length is growing, and also the output token length is growing. And so all of these play into, ultimately, the marketing and the pricing of future tokens. Tokens are the new commodity, and like all commodities, once it reaches an inflection, once it becomes mature or becomes maturing, it will segment into different parts. The high throughput, low speed could be used for the free tier. The next tier could be the medium tier. Larger model maybe, higher speed for sure, larger input context length. That translates to a different price point. You could see from all the different services, this one is free, it's a free tier. The first tier could be $3 per million tokens. The next tier could be $6 per million tokens. You would like to be able to keep pushing this boundary because the larger the model, smarter. The more input token context length, more relevant. The higher the speed, the more you can think and iterate smarter AI models. So this is about smarter AI models. And when you have smarter AI models, each one of these clicks allows you to increase the price. So this is $45. And maybe one day there'll be a premium model that allows you, a premium service that allows you to generate token speeds that are incredibly high because you're in a critical path, or maybe you're doing really long research, and $150 per million tokens is just not a thing. So let's translate that. Suppose you were to use 50 million tokens per day as a researcher at $150 per million tokens. As it turns out, as a research team, that's not even a thing. So we believe that this is the future. This is where AI wants to go. This is where it is today. It had to start here to establish the value and establish its usefulness and get better and better and better. In the future, you're going to see most services encompass all of that. This is Hopper. Hopper started, and I moved the chart. This is 50, this is 100. Hopper looks like this. And you would have expected Hopper, the next generation, to be higher, but nobody would have expected it to be that much higher. This is Grace Blackwell. What Grace Blackwell did is, at your free tier, increase your throughput tremendously. However, where you mostly monetize your service, it increased your throughput by 35 times. This is no different than any product that every company makes. The higher the tier, the higher the quality, the higher the performance, the lower the volume, the lower the capacity. And so it is no different than any other business in the world. And so now we're able to increase this tier by 35x. And we introduced a whole new tier. This is the benefit of Grace Blackwell, a huge jump over Hopper. Well, this is what we're doing with so this is Grace Blackwell. Okay, let me just reset this. And this is Vera Rubin. Okay? Now just think what just happened. At every single tier, we increase the throughput. And at the tier where your highest ASP and your most valuable segment, we increased it by 10x. That is the hard work. This is incredibly hard to do out here. This is the benefit of NVLink 72. This is the benefit of extremely low latency. This is the benefit of extreme co-design, that we can shift the entire area up. Now, what does it mean from a customer perspective in the end? Suppose I were to take all of that and I just multiply it against, suppose I took 25% of my power, used it in a free tier, 25% of my power in the medium tier, 25% of my power in the high tier, and 25% of my power in the premium tier. My data center only has a gigawatt. And so I get to decide how I want to distribute. The free tier allows me to attract more customers. This allows me to serve my most valuable customers. And the combination, the product of all that, allows you basically your revenues. The revenues you can generate, assuming this simplistic example, allows Blackwell to generate 5 times more revenues. Vera Rubin to generate 5 times. Yeah. So Vera Rubin, you should get there as soon as you can. And the reason for that is because your cost of tokens goes down and your throughput goes up. Now, but we want even more. And so let me just show you back to this. This is, as I told you, this throughput requires a ton of flops. This latency, this interactivity requires enormous amount of bandwidth. Computers don't like extreme amount of flops, extreme amount of bandwidth, because there's only so much surface area for chips that any systems has. And so optimizing for high throughput and optimizing for low latency are, in fact, enemies of each other. And so this is what happened when we combined with Grok. Okay? And so we acquired a team that worked on the Grok chips and licensed the technology, and we've been working together now to integrate the system. This is what that looks like. So at the most valuable tier, we're now going to increase performance by 35x. Now this very simple chart revealed to you exactly the reason why NVIDIA is so strong in the vast majority of the workloads so far. And the reason for that is because up in this area, throughput matters so much. NVLink 72 is so game-changing. It is exactly the right architecture, and it's even hard to beat, even as you add Grok to it. However, if you extended this chart way out here, you said you wanted to have services that delivers not 400 tokens per second, but 1,000 tokens per second, all of a sudden, NVLink 72 runs out of steam and it simply can't get there. We just don't have enough bandwidth. And so this is where Grok comes in, and this is what happens when we push that out. So it goes out beyond, thank you. It goes out beyond even the limits of what NVLink 72 can do. And if you were to do that, translate that into revenues, relative to Blackwell, Vera Rubin is 5x. If most of your workload is high throughput, I would stick with just 100% Vera Rubin. If a lot of your workload wants to be coding and very high valued engineering, token generation, I would add Grok to it. I would add Grok to maybe 25% of my total data center. The rest of my data center is all 100% Vera Rubin. And so that gives you a sense of how you would add Grok to Vera Rubin and extend its performance and extend its value even more. This is what happens. This is a contrast. The reason why Grok was so attractive to me is because their computing system, a deterministic data flow more complicated than this, it's multidimensional, but you'll be studying the throughput and the token speed of your AI factories. The throughput, token speed at ISO power, because that's all the power you have, throughput and token, the context length, depending on the different grades of, because that's all the power you have, throughput and token speed for your factories forever. And that analysis is going to lead directly to your revenues. What you do this year will show up precisely next year as your revenues. And this chart is what it's all about. And I said, on the vertical axis, thank you guys, on the vertical axis is throughput, on the horizontal axis is token rate. Today, I'm going to show you this. Because we're now able to increase the token speed, and because model sizes are increasing, because the token length, the context length, depending on the different grades of different application use case, continues to grow from maybe 100,000 tokens input length to maybe millions. The token input length is growing, and also the output token length is growing. And so all of these play into, ultimately, the marketing and the pricing of future. It's a free tier. The first tier could be $3 per million tokens. The next tier could be $6 per million tokens. You would like to be able to keep pushing this boundary because the larger the model, smarter. The more input token context length, more relevant. The higher the speed, the more you can think and iterate. Increase the price. So this is $45. And maybe one day there'll be a premium model that allows you, a premium service that allows you to generate token speeds that are incredibly high because you're in a critical path, or maybe you're doing really long research. $150 per million tokens is just not a thing. So let's translate that. Suppose you were to use agentic AI systems. It's based upon this idea. This is a contrast. The reason why Grok was so attractive to me is because their computing system, a deterministic data flow processor, it is statically compiled. It is compiler scheduled, meaning the compiler figures out when of extreme differences, one for high throughput, one for low latency. It still doesn't, Grace Blackwell, early sampling of it was really complicated because of coming together NVLink 72, but the sampling of Vera Rubin is just going incredibly well. And in fact, Satya, I think, texted out already that the first Vera Rubin rack is already up and running at Blackwell is here, the Oberon system. In the case of Rubin, we have the Oberon system. We're always backwards compatible so that if you wanted to not change anything and just keep on moving through incredible new technology, now uniting the scale of NVIDIA and the graphics, that can't happen. We're building super complex systems.
Power management between the grid.
Talking about is gigantic. We call this the NVIDIA DSX platform. And just as all of our platforms, there's the hardware layer, there's the library layer, and there's the ecosystem layer. It's exactly the same way. Let's show it to you.
The greatest infrastructure build-out in history is underway. The world is racing to build chip, system, and AI factories, and every month of delay costs billions in lost revenues. AI factory revenues are equal to tokens per watt. So with power constraints, every unused watt is revenue lost. NVIDIA DSX is an Omniverse digital twin blueprint for designing and operating AI factories for maximum token throughput, resilience, and energy efficiency. Developers connect through several APIs. DSX Sim for physical, electrical, thermal, and network simulation. DSX Exchange for AI factory operational data. DSX Flex for secure, dynamic power management between the grid. And DSX Max Q to dynamically maximize token throughput. It starts with SIM-ready assets from NVIDIA and equipment manufacturers, managed by PTC Windchill PLM. Then, model-based systems engineering is done in Dassault Systems 3D Experience. Jacobs brings the data into their custom Omniverse app to finalize design. It's tested with leading simulation tools, using Siemens Star CCM Plus for external thermals, Cadence Reality for internal, ETAP for electrical, and NVIDIA's network simulator, DSX Air.
Our world. We didn't know many of you just a couple years ago, and now we're working so close together to work on and build together the. Peter Steinberger's here, and he's complicated to do so. We're working with our partners on a new computer called Vera Rubin Space One, and it's going to go out to space and start data centers out in space. Now, of course, in space, there's no conduction, there's no convection, there's just radiation, and so we have to figure out how to cool these systems out in space. But we've got lots of great engineers working on it. Let me talk to you about something new. Build together the. It's going to go out to space and start data centers out in space. Now, of course, in space, there's no conduction, there's no convection, there's just radiation. Conduction, there's no convection, there's just radiation. And so we have to figure out how to cool these systems out in space. But we've got lots of great engineers working on it. Let me talk to you about something new. A few weeks. It exceeded what Linux did in 30 years. And it's that important. It is that important. It will do, well, this is all you do, okay? We're announcing our support of it. Let me just quickly go through this. I want to show you a couple things. You simply type this. You type this into a console, and it goes out, it finds OpenClaw, it downloads it, it builds you an AI agent, and then you could tell it whatever else you need to do, okay? So let's take a look.
An open source project just dropped. Andre Carpathian just launched something called Research is a huge deal.
You give an AI agent a task, go to sleep, it runs 100 experiments overnight, keeping what works and killing what doesn't.
I really love what my stuff enables that person to do. And we had like one guy, he told me like he installed it at his 60-year-old dad, and like they make beer, connected the machine via Bluetooth to OpenClaw. And then we automated everything, including the whole website for people to order.
Lobsterlager fertig sein.
Hundreds of people are queuing up for lobsters in Shenzhen.
OpenClaw.
OpenClaw. You want to build OpenClaw with OpenClaw.
Everyone is talking about OpenClaw, but what is OpenClaw?
Believe it or not, there's already a claw con. Incredible, incredible. Now, I illustrated effectively what OpenClaw is in this way, so that all of you can understand it, but let's just think what happened. What is OpenClaw? It connects, it's an agentic system. It calls and connects to large language models. So the first thing it has resources that it manages. It could access tools, it could access file systems, it could access large language models. It's able to do scheduling. It's able to do cron jobs. It's able to decompose a prompt that you gave it into step by step by step. It could spawn off and call upon other sub-agents. It has I/O. You could talk to it in any modality you want. You could wave at it and it understands you. You could talk to any modality you want. It sends you messages. It texts you, sends you email. So it's got I/O. What else does it have? Well, based on that, you could say, in fact, it's an operating system. I've just used the same syntax that I would describe an operating system. OpenClaw has open-sourced, essentially, the operating system of agentic computers. It is no different than how Windows made it possible for us to create personal computers. Now OpenClaw has made it possible for us to create personal agents. The implication is incredible. The implication is incredible. First of all, the adoption says something all in itself. However, the most important thing is this. Every single company now realizes, every single company, every single software company, every single technology company, for the CEOs, the question is, what's your OpenClaw strategy? Just as we need to all have a Linux strategy, we all needed to have an HTTP, HTML strategy, which started the internet. We all needed to have a Kubernetes strategy, which made it possible for mobile cloud to happen. Every company in the world today needs to have an OpenClaw strategy. Earlier, the way enterprise IT works, and the reason why it's called data centers is because these large rooms, these large buildings, held data, held the files of people, the structured data of business. And that turns into tools that humans would use. Digital workers would use. That is the old IT industry. Software companies creating tools, saving files, and of course, GSI's consultants that help companies figure out how to use these tools and integrate these tools. These tools are incredibly valuable for governance and security and privacy and compliance, and all of that continues to be true. It's just that post-OpenClaw, post-agentic, this is what it's going to look like. This is the extraordinary part. Every single IT company, every SaaS company will become a gas company. No question about it. Every single SaaS company will become a gas company, an agentic as a service company. And what's amazing is this, OpenClaw gave the industry exactly what it needed at exactly the time. Just as Linux gave the industry exactly what it needed at exactly the time, just as Kubernetes showed up at exactly the right time, just as HTML showed up. It made it possible for the entire industry to grab on. Agentic systems in the corporate network can have access to sensitive information, it can execute code, and it can communicate externally. Just say that out loud, okay? Think about it. Access sensitive information, execute code, communicate externally. You could, of course, access employee information, access supply chain, access finance information, sensitive information, and send it out, communicate externally. Obviously, this can't possibly be allowed. And so what we did was we worked with Peter. We took some of the world's best security and computing experts, and we worked with Peter to make OpenClaw, enterprise secure and enterprise private capable. And we call that, this is our NVIDIA OpenClaw reference for NemoClaw, which is a reference for OpenClaw, and it has all these agentic AI toolkits, and the first part of it is technology we call OpenShell that has now been integrated into OpenClaw. Now it's enterprise ready. This stack with a reference design we call NemoClaw, okay? With a reference stack we call NemoClaw, you could download it, play with it, and you could connect to it the policy engine of all of the SaaS companies in the world. And your policy engines are super important, super valuable. So the policy engines could be connected. NemoClaw or OpenClaw with OpenShell would be able to execute that policy engine. It has a network guardrail. It has a privacy router. And as a result, we could protect and keep the claws from executing inside our company and do it safely. We also added several things to the agentic system. And one of the most important things you want to do with your own custom claws is so that you can have your custom models. And this is NVIDIA's Open Model Initiative. We are now at the frontier of every single domain of AI models. Whether it's Nemotron, Cosmos World Foundation model, Groot, artificial general robotics, humanoid robotics models, AlphaMyo for autonomous vehicle, BioNemo for digital biology, Earth-2 for AI physics. We are at the frontier on every single one. Take a look.
The world is diverse. No single model can serve every industry. Open Models is one of the largest and most diverse AI ecosystems in the world. Nearly 3 million open models across language, vision, biology, physics, and autonomous systems. Open Models is one of the largest and most diverse AI ecosystems in the world. Nearly 3 million open models across language, vision, biology, physics, and autonomous systems enable AI builds for specialized domains. NVIDIA is one of the largest contributors to open source AI. We build and release 6 families of open frontier models, plus the training data, recipes, and frameworks to help developers customize and adopt. New leaderboard topping models are launching for every family. At the core, Nemotron, reasoning models for language, visual understanding, RAG, safety, and speech.
Can you hear me now?
Yes.
Hello?
Yes, I can hear you now.
Cosmos, frontier models for physical AI world generation and understanding. Alpamayo, the world's first thinking and reasoning autonomous vehicle AI. Group, foundation models for general purpose robots. BioNemo, open models for biology, chemistry, and molecular design. Earth 2, models for weather and climate forecasting, rooted in AI physics. NVIDIA open models give researchers and developers the foundation to build and deploy AI for their own specialized domains.
Our models, thank you. Our models are valuable to all of you because number one, it's on the top of the leaderboard. It's driving cars and reasoning, and of course. But most importantly, it's because we are not going to give up working on it. We're going to keep on working on it every single day. Nemotron 3 is going to be followed by Nemotron 4. Cosmos 1 was followed by Cosmos 2. Groot at Generation 2. Each and one of these, we're going to continue to advance these models. Vertical integration, horizontal openness, so that we can enable everybody to join the AI revolution. Number one on leaderboard, the intelligence you need. This is Nemotron 3 Ultra. It is going to be the best base model the world's ever created. This allows us to help every country build their sovereign AI. And we're working with so many different companies out there. And one of the most exciting things that we're doing today, I'm announcing today, is a Nemotron coalition. Has some amazing companies in it. Black Forest Labs, Imaging Company, Cursor, the famous coding company, we use lots of it, LangChain, billion downloads for creating custom agents, Mistral, the Arthur mentioned, I think he's here, incredible company, Perplexity's. I said that every single enterprise company, every single software company in the world needs an agentic systems, need an agent strategy. You need to have an open cloud strategy, and they all are more productive. And those tokens could use that is optimized, it's performant, it is safe and secure. Training computer, the synthetic data generation and simulation computer, and of course the robotics computer that sits inside the robot itself. We have all the software stacks necessary to do so. As much energy as possible and increase the amount of fidelity as possible. There's so many humanoid robots here, but one of my favorites is a Disney robot. You know what? Tell you what, let me just show you some of the videos. Let's look at that first.
The first global rollout of physical AI at scale is here. Autonomous vehicles. And with NVIDIA Alpamayo, vehicles now have reasoning, helping them operate safely and intelligently across scenarios. We ask the car to narrate its actions. They generate massive amounts of synthetic data and Isaac Lab for training and data generation. Foxconn fine-tunes group models in Isaac Lab, as does Noble Machines.
Close it out. Of course. All right, play it. Come on.
Terminating simulation.
Hello? Anybody here?
The keynote's over, all was said, Jensen mapped the road ahead. AI factories coming alive, agents learning how to drive, from open models to robots too. Now we'll break it all down for you. Compute exploded, what we saw from CNNs to OpenClaw. Agents working across the land, but they need the power to meet demand. So we solved the problem, it was brilliant. We multiplied compute by 40 million. Once upon an AI time training was the paradigm. Sure, we're talking models how, but inference runs the whole world now. Vera shows us who's the boss at 35 times less the cost. Blackwell makes the tokens sing NVIDIA, the inference king. AI factories, once took years, vendors pulling racks and gears. Built up slowly piece by piece, no clear way to scale this beast. DSX and Dynamo know what to do. Turning power into revenue. Agents used to wait and see, now act autonomously. But if they ever try to stray, safe off, block and say no way. Nemo calls there to guard the course. And yes, my friend, it's open source. Cars that think and droids that run, this ain't the movies, it's all begun. How come I will call the shots? It's a GPT moment for the bots from sim to streets. Now watch them drive. Throw your hands up for physical AI. Industrial age built what came before, now we build for AI. Even more, Veracruz plus Grok make the inference splash. Put them together, now it's raining cash. We build new architecture every year, cause claws keep yelling more tokens here. The AI stacks for all to make, so let us all eat 5 layer cake. The moment's bright, the path is clear, cause open models led us here. When data's missing, there's no dispute. We just generate more with compute. Robots learning without flaw, fueling the 4 scaling laws. The future's here, won't you come and see? Welcome all to GTC.
All right, have a great GTC! Wave. Thank you, everybody. See you, love.
I just met.
To GTC, I am Carlo Fisicaro, Chief Technology Officer at Peptone, and today with Michele Invernizzi, Senior Scientist here at Peptone, I'm going to talk about how to target proteins, how we at Peptone drug them, and a new model, a generative AI model we developed to generate their structures, their ensemble, and evaluate performance of ensemble generators in general. In the first part of this talk, I'm gonna describe what the challenge is about, what are these other proteins, why we do care about it. And in the second part of the talk, Michele Invernizzi will talk about how this model works, how we managed to develop it, its performance, and the related benchmark. Peptone is a drug discovery company, a biotech company, focused on drugging a peculiar class of proteins called intrinsically disordered. And we are based in the UK, where our headquarters is, and in Switzerland. Our investors are Bessemer Venture Capital, F Prime, Oxford Ventures, Novartis, and Walden Catalyst. Now, IDPs, intrinsic disordered proteins, represent roughly 30% of the human proteome. That is the protein that can be expressed by the human genome. And they are involved in terrible diseases.
Hello, everybody. My name is Sandra. I manage robotics partners at NVidia. Today, I have the pleasure of putting together this panel with a few of our partners based in the EMEA region. The title of the panel is going to be Build Physical Intelligence Open Collaboration
Hello everyone and welcome to European Robotics Startup Showcase at NVidia.
Embodiment to get still required.
How they want. He'll discuss how they are transforming agriculture into data-driven operation using smart sensors and robotics to tackle global food challenges. Then we'll see how robots are entering our daily life.
Vegetables across the globe, we move production closer to do physical AI very close to the farming environment, and we can truly see what works and beyond labor shortage and transported to Germany. It is not any plant on the field and in real world models. And we have developed ways to build vision models, tactile models, language and action models from human demonstrations, as we have seen in the previous presentation, specifically for plants. And NVIDIA accelerates our journey and this pipeline, where we are about to launch several robo-fields as training gyms across Germany and beyond. Agriculture has many challenges, but there might be one ultimate solution, the humanoid, to solve many, many problems at once. At the core, you see a humanoid torso, no head, no legs, no dancing, just hands and eyes, and a holistic system approach. We start with AI vision models, enabling robots to understand crops, plants, tools, and the environment. AI tactile sensor models help the hands to feel contact, to feel temperature, to feel moisture, and the AI language domain models encode agricultural knowledge and task descriptions and intent. All this feeds into AI robot action models.
Or teleoperated deployment in real world. It takes years to accumulate sufficient cases, working with customers in phase that combines live 3D mesh streaming with XR digital twin control, enabling that gives accurate sense of depth, which is critical for intuitiveness, speed, and dexterity when operating robots beyond
without being teleoperated ready across Europe
environment. And once we train one robot
together, building fulfillment center drone and drone delivery systems. We are working alongside people in live hotels environment already across Europe. We did that in Rome, in Paris, in Berlin, and we work alongside hotel staffs in big brands such as Hilton and Marriott. Our hotel's environment. It's easy for us because we are deployed. Then we create a pipeline of a complete hotel environment. And these models are running daily. When we want to improve throughout RL, it's easy for us because we are deployed with already more than 10 robots in live and exactly where we are at. If the laundry porter would like to take a cart, then the cleaner will call him and say, hey, can you please take the cart? It's full downstairs. And we understood that in order for Billy to help understanding that and get out, he's also very aware. So when people, and we will
correct their own mistakes. In terms of use cases, we are working at the moment mostly in assembly and kitting, as well as in packaging and sorting use cases. We work together with globally leading corporates to automate these high-volume industrial applications across verticals that mostly involve manual labor that is currently done by people today. This is an example of an actual project that we have recently deployed, which is essentially a very complex automotive assembly tasks in collaboration with Audi. Here is our bimanual robot setup in a completely autonomous end-to-end policy, currently playing at 1x speed, essentially purely from vision and states to actions, able to essentially perform this very complex insertion task completely autonomously, using our end-to-end learning pipeline based on real-world human data. From now on, the video is sped up, and you can see how the robot is essentially able to continue this type of assembly task in a very repeatable way, despite it being fundamentally like an end-to-end AI model. This project is essentially one sneak peek into our type of collaborations in assembly use cases that are ongoing today and being deployed across industries, starting from Europe. We have essentially a training pipeline in which we train robots in an easy fashion, solving the data problem with higher of human behavior, and has exactly selling this end-to-end solution based
We have deployment, and with this, I thank you very much.
Into the future. And this is particularly true in Italy, which is going to basically, it is expected to cut its population and in terms of physical and cognitive capabilities by taking a look how human-centered attributed the highest number of new humanoid robots in the world. So we've been after humanoid robots worldwide, which was not really on data generation systems. So we also were able to basically make with a degree of autonomy. And this is basically a robot. The products are basically three. We want to humanoid robot dealing with a patient in healthcare, and this is not so. We believe that we have to build this open released represent enable motor level and manipulation level. Things are creating the first vertical, our welding line for welding being developed thanks to the NVIDIA tools. For sure, all the reinforcement learning, both at the motor level and manipulation level, it is enabled by the NVIDIA tool.
Physical AI. Robots learn to handle complex tasks.
France and Benelux here at NVIDIA, and I'll be your host for this session with three of my major invitees for
how do you
ground helping
access to capacity, but how those capacities are managed, batch versus interactive, this Slurm versus Kubernetes, etc., etc. These are very low in NVIDIA or
GTC2026 を上げているディープテック企業となります。自動運転に資するあらゆるテクノロジーを開放し、様々な組織、個人がその発展に貢献できる持続的なエコシステムを府県で39カ所、市区町村で言いますと103の自治体で推進させていただいております。これは膨大かつ多様であり、効率的な MLOps の実現が大きな課題となっております。このような状況を鑑みまして、プロジェクトでは10万キロを超えた収集では、この DRS を使って逆的に加速させることができます。また、高 MLOps の枠組みにおいて、AI を効率的に行くためには、リッチかつ正確なデータ収集が必要不可欠です。弊社では、リッチなデータを収集するために、高解像度かつサラウンドのステーションに富んだデータがこのプラットフォーム上で入手可能となっております。 ただし、この大量かつ多様なデータを管理する。ここからは実際にコスモスを活用理解を付与することができる大きな問題となっております。未発見のエッジケース利用が必要不可欠です。しかし、現実世界の走行データは一般的なシナリオに偏っており、重大なエッジケースの発生頻度は極めて低いため、これらのエッジケースを網羅的に収集することは困難です。これはロングテール問題として自動運転分野で大きな問題となっております。未発見のエッジケースはシステムの安全性、機能的なワークフローをご紹介いたします。この課題を対処するためにセミアノテーションが備わらないようにすることが可能で、利用セミアノテーションを通じてある落下物で存在するシーン、エッジケースのラベル生成を実現することが可能です。当然ながらこのプロセスを繰り返し行うことにより、エッジケースに対しても自動でラベリングが付与可能となってきます。例えばこのようなケースとなります。次のスライドではいくつかのコスモスプレディクトで生成された困難なシナリオをセミアノテーションを通じてラベリングしている事例を紹介させていただきます。左上は鹿が存在するシーン。左下がイノシシに接近するシーン。中央上は路上に謳歌している人物に接近するシーン。中央下は鏡ながら犬とコミュニケーションしている人物がいるシーン。右上は落下物であるはしごの手前で停止するシーン。右下は落下したタイヤの手前で停止するシーンとなります。横断するシーンなどもオートラベリング対応可能になってきております。これが合成データではなく、実際の取得データに対してのオートラベリングした結果となります。左側の人が横たわる例で完全にラベリングできており、右側ですと横断歩道を通過する犬も正確にラベリングできております。コスモスプレディクトとこのセミアノテーションによるラベル付きデータ生成を通じて、高エムロップスのオートラベリング基盤のせいで網羅的に書けます。こんな環境条件をもフォーカス的に書きます。収集した走行的にバリエーションに富んだデータセットのただし現在オープンになっているマジで信号の状態に応じたまた、学習のためのデータオーギュメンテーションのみならず、シミュレーションで得られたテスト用データへのコスモストランスファーの活用も進めております。任意のシミュレーターでマスクと画像のペア動画を作成し、コスモストランスファーを通じてテストデータに使えるようなフォトリアリスティックな動画の生成についても取り組んでおります。この例にあるように、距離ごとのドスで作った。それでは本発表をまとめさせていただきます。NVIDIA Cosmos を活用した高 MLOps 基盤では、自動運転開発の課題解決に向けてフィルタリング、世界モデルを利用して物販による高度なデータ拡張です。この機能は高 MLOps のデータセット
everyone.
I'm Colin Payne. I'm the Head of Innovation at the UK's Financial Conduct Authority, and I'm really pleased to be. My work, consumer protection. They include tool access, they include orchestration. All of these things have to be there. So it isn't that the firms lack ideas, it's just that many really struggle to generate the kind we wanted to engage with all of the real-world financial transactions. We've got customer profiles and so on. As you'd expect, that enables safe development at scale. But I'll tell that in just a second, but I just wanted a mirroring guidance, and that would help us turn these prototypes into real evidence for the future. And then, of course, we've got accelerated development. And this was through strategic partnerships. We had all of this supercharging coming together. So you had this real, absolute global first, enterprise for our thinking. Now, when we dive into the architecture of what's behind the sandbox, this is just a very simplified diagram for everyone to be able to understand. But this is the core of the success. The sandbox was never going to be a concept. It's a full stack designed to remove that POC to production gap. And the audit surface you need for sensitive information, multiple data slices, while still being governed to the high standards that we expect. What's the failsafe? All of those things are absolutely critical. The goal was not to maximize. They were really vibing on what we were doing, and the announcement came out that we were going to be doing this work with the NVIDIA support. But it was absolutely stunning, the response we had. Imagine we announced at London Tech Week. Jensen was on stage. We had the Prime Minister of the UK. They were really vibing on what we were doing, and the announcement came out that we were going to be doing this work with the NVIDIA support. My LinkedIn went absolutely nuts, to be honest. It was one of the most extraordinary responses to anything I put out there. It was genuinely viral, and the application process was easy, and it attracted a huge number of applications. Now, maybe 132 doesn't sound like a big number, but if you consider usually we will get 130 or so coming through our services every year or two. So this was for one cohort, which we would normally have maybe 20, the really big starting and completing. I'll just give you a bit of a flavour.
Into the FCA and get access to our data, as well as to...
The idea is you have a sandbox environment where people can come in,
mentorship, all in that.
I guess I'd like to, at that kind of point, really
actually create during our time, unfortunately, and also. So for us, accuracy really wasn't enough, actually exposing real customers. So what we were able to use this in the FCA viewpoint, where we started with a single generalized agent, end-to-end, what we create.
From a systems point of view, also works without this interface.
Needs, right? I mean, and I love your
escape, and I think one of the key bits for us, one of our
And welcome everybody. Thanks for joining this GTC panel. And we're going to talk today about AI. AI is definitely moving beyond individual initiatives today. It's really becoming foundational infrastructure. Much like electricity and the internet before it, AI factories are now emerging as the engines that turn data into intelligence at scale. And across Europe and beyond, this marks the beginning of a new industrial transformation. AI factories are becoming strategic national assets, shaping productivity, innovation capacity, economic growth, and long-term competitiveness. And in this race, speed does matter, as we'll hear from our panelists. Time to first token is becoming a defining metric. How fast you move from installation to production, and how do you go beyond talking and go from ambition to execution. At NVIDIA, we often describe AI as a 5-layer cake. All these layers. You have the energy, you have chips, you have multiple chips, not just one. You have infrastructure, you have models, and you have the applications on top. And AI factories integrate all 5 layers into a complete system. Data goes in, intelligence comes out. And so sovereign AI is not just about isolation. It's really about participation. It's about enabling nations and industries to compete globally while retaining control over data, models, and value creation. And today we'll explore how this is being built in practice, what it takes to scale, where the bottlenecks are, and how strong partnerships allow us to go faster and further together. Now, let me introduce you to our panelists here. We have Peter. Peter represents T-Systems, where sovereign AI becomes real for large enterprises and the public sector. We saw an amazing
Welcome to the session Beyond the
Yes, thanks a lot, David, for the opportunity. Super happy to be here on this fantastic panel. My name is Eric. I'm the Chief Research and Technology Officer at Okin, a company I've been with for now a bit more than 4 years. And so Okin is a French-American startup.
Vision really is to build AI frontier systems that allow up
A couple of other use cases.
Good afternoon, good morning, good evening, everyone, and welcome to our GTC panel and touch on different.
We work in three main areas. The first area is the de novo functional design of materials, functional materials, things for energy applications and other chemistry applications using computational chemistry, in silico design, as it were. We also work on essentially.
I am a professor of computer science at
chemists that can use machine reasoning and computational.
Our lab focuses on different decision making, where you have societies of agents that are potential.
Introduction and invitation to be part of this panel. I am Oyaceli Liktutan, and I am a reader in AI and robotics and social science. Recently, we have been looking at continual imitation learning, how robots can learn new skills over time, and this is very important for long-term autonomy. And the second project is focusing on more about how we can use large language models and vision language models in a sense to understand multiple operation and end-of-life processes. And in particular, within the scope of this project, we are focusing on generative digital twins, especially how we can simulate failure modes and also generate synthetic data for predictive maintenance. And taken together in our lab, we are very much interested in.
Now part of Solve. This is related to basically using subsets of modules within a neural network or parts of the implementation of our flagship.
Perhaps see lots of computing decisions interact.
By these LLMs
being very.
And in simulate for the introduction and invitation to be part of this panel. I am Oyaceli Liktutan.
Hello everyone, and welcome to this session about agentic AI for the next generation financial advisors. My name is Nicolas Mock. I'm head of SEBX, the innovation studio of the bank SEB, and together with my research lead Anastasia Varova, we will go through this presentation about collaboration between SEB, the bank, and NVidia. The presentation will consist of three parts. The first one about the SEB and NVidia collaboration, a little bit of background about the consortium and how we managed to work together between NVidia and SEB. I will then go through the business view, the financial analysis view of the case. And Anastasia will, after a short demo, go through the solution and the technical details. Starting with the SEB and NVidia collaboration, at least for us in SEB, this is a bit of a new and pioneering type of collaboration. But let me give you some background about what SEB is, as many of you might not know. So SEB is a leading Nordic bank in the Nordic countries, so present in 20 countries, but with home markets in Sweden, Norway, Finland, the Baltic countries, Germany, and the UK. The core of the bank, the history of the bank, is very much around large businesses and businesses in my part as people that we can use to co-create, because as for us it is a new journey. We don't know how to use these things from day one, so we need quite a bit of help. I will start with the last bullet point from my part as more of a banker. In particular are going to change a lot of things. So we discussed with a number of our client executives, and I said, yeah, that's the part that is where there is most value to be adding to my conversation, to the client executive conversation, to the corporate client. And you need insight, you need relevance, and doing it at scale is quite difficult. So as you see here, the case is also bundled with a number of efficiency things, right? It's not purely let's do something completely new and new solutions, but on the other hand, you also see that by having a very rich conversation between the client executive and the corporate client, that would also open new areas of collaboration and sales for us, where we could sell new products, advise our corporate client in a better way, and very much about how can we put both some automation but also some added value like predictive modeling and scenario analysis, for example, in the mix. So we built an agentic system for financial analysis that basically automates and simplifies the tasks that were on the previous slide. Consuming, you want to maybe narrow down on, okay, but what happens if, and what happens if that happens, and how does it impact my system, in order to have a customized view of the analysis. One important point for us is also to capture, I mean, we hear a lot that AI is nothing without data, and the discussion between a client executive and its corporate client, or the internal dialogue the client executive has about his client while preparing, is a very important data that we, for natural reasons, don't have dialogue with the corporate, with the billionaires. So those are quite important numbers, and we did not even count there what I was talking about, which is if we can predict probability of default of our client, if we can which is a competitive alternative to having the same tools as all the other competitors, which drives me to the last part, which is we think that credit and advisory are the core of the bank's business, and if we can invest in AI in order to do this more intelligently, more proactively, and with more predictive power, into the realm of prediction. And prediction is very important for us because it helps us in the dialogue with the customer, but it helps us being proactive when something happens. And that can be, we have chosen risk management on this slide, but it can be also, we see that you're growing quite fast. Maybe an acquisition is in order, or maybe you could use this very customized
for first-time users,
the technical
through the main workflow and features of the Midcorp tool. For first-time users, we can start on the login page. The folder that is directly linked to your user account. You can add. The research plan consists of a set of goals and deliverables. Also possible to go with follow-up queries. That was all I had that we can deploy on AI Factory and scale across different use cases. AI Factory, the software layer, and we'll talk a little bit about our choices in use cases, really available through where we incorporate internal and external. Those are overall interactive planner agent, first on AI Factory, and most importantly, it allows to agentic workflows from day one. So as I mentioned before, contain tables and charts, and the table as possible to make sure that our not very well structured, so that typically actually adequate and related to the business needs. And the type of documents that we typically work with at SEB look something like this. So it's complex PDF documents that contain tables and charts, and the tables are usually not very well structured, so the structure can charts. And here we wanted to cover a broad they typically chunks from the benchmark, and it can be especially if K is smaller. But then the adjusted recall actually helps us see that NIM Retriever slightly outperforms Track Engine, which means that it actually provides us a competitive alternative to a proprietary solution. So it means that, for example, NIM Retriever can be used not just in this use case, but in general in a variety of. So the kind of key takeaways here is that all of this work is business relevant benchmarks.
root assisting this failure but you want to have it voice enabled.
You through payments and how Adyen works. So Adyen is one of the largest payment providers in the world. The appropriate ISO message instrument. We can perform fraud risk checks. We can perform authentication in case it's required for fraud or regulatory reasons. And then we optimize the payment where possible with techniques such as routing. Behind the scenes, there's typically a payment request to the appropriate ISO message for the designated payment method, which is either to a card scheme or a local payment method. So all of this is happening in real time, where Adyen is ultimately looking to receive an authorization from the cardholder's issuing bank. After this entire authorization operation, we start moving money in the background so that our merchants receive the funds for goods and services provided as soon as possible. So merchants kind of face three main objectives with this. So they face a complex challenge, right? And they have these three main goals. We can show the payment method module that ranks the different payment methods shown to users at the merchant checkout page. For example, we can show local payment methods when the merchant wants to have the lowest cost possible. Or maybe we can show the payment method at the top, which is most likely to convert for that specific user if the merchant wants to maximize conversion. We then have a module called Tokenize, where we can swap the credit card details sent with network tokens sent by card schemes. And we replace them with these network tokens, which are considered safer and therefore more likely to convert. Network tokens are generated per merchant so that if such a token would leak, the actual card number behind the token is not exposed. We can also apply real-time account updating to ensure that we basically have the correct card details for a given card, even if that card is expired. Then we have a module called Protect, and if a merchant basically gives us the license, we can apply our own fraud detection systems to then understand the risk of fraud. Then we have Authenticate. We can apply, based on that risk score that I mentioned, we can apply a risk-based authentication. For example, we've invested in lots of cost optimization in terms of running, have observed either through global or domestic networks. So the impact of this work across each transaction based on conversion and cost. For example, we've invested in lots of direct connections with local debit networks early on in markets like the US and Australia. And for dual branded debit cards, we can actually route the payment either through global or domestic networks. So the impact of this work across the board has meant that our products deliver really significant conversion uplift for our clients in terms of payments alongside other benefits. So our overall product suite, this product suite has led to about a 1.2% extra uplift on conversion rates. On personalized itself, pilots that we've been running have observed conversion rate improvements of up to 6% using this personalized optimization. On fraud detection, using that reduction in rules-based blocking, we've led to an overall about 10% increase in conversion using machine learning and a 41% drop in fraud rates. And for cost optimization in terms of optimize and that routing system, we've led to cost savings of up to 20% in the US and actually an 89 basis point improvement in authorization rates in the US alone. So I'm going to focus just on one of these modules in the coming slides, which is our optimize module, and talk through what we've been doing there. Let's talk through contextual bandits within payments, focusing on that optimize module. So payments optimization is a fundamental context band, but contextual bandit problem. Every transaction that we have arises with a really rich high-dimensional state, including the merchant's payment configuration, bank identification number, and its associated metadata, such as, for example, like if it's a prepaid or standard card, if it's a commercial versus consumer transaction, it's a credit versus debit transaction, the issuing bank involved, that issuer's identity and regulatory region, the amount of retries that transaction has had, and a bunch of different behavioral signals, even at checkout, that we know about from the actual shopper. We then choose a structured action consisting of a routing path, an authentication strategy, and a specific ISO message configuration that's sent in the payment. The reward that we have is stochastic, right? It's the issuer's authorization decision, and it comes from that issuer's internal risk engine that we don't know about. So this isn't just static prediction, it's about policy learning over interventions. The key things here is that exploration has a direct economic cost, right? Whenever we actually change some of these ISO messages or the routes that we take in an online setting, we are actually affecting the conversion rates of that customer in real time. So we need to be very careful about the level of experimentation that we run. Also, issuer behavior drifts, it changes all the time, how banks think about different ISO messages and routes and the risk of payments. Also, this action space is constrained, right? We can't change these payment messages all the time. There's regulatory considerations. And so once we frame payments in this way, the key question is how can we actually optimize? So what do we actually optimize here? So Adyen views payments as a really complex optimization problem, aiming to maximize the expected approval rate for every transaction, navigating thousands of these independent bank risk profiles, right, and their risk models. The primary lever that we have is intelligent routing. So that's kind of consists of two main things. We can do inter-scheme routing. So for dual branded cards, so for example, if you have a card that has MasterCard and a Star logo, or Visa or Dancorp, we can select the network, either MasterCard or Star, which has the best combination of approval chances and the lowest fees, right, depending on what you choose to prioritize. Then we can also do inter-acquirer routing, where essentially for a single branded card, we as Adyen, the payment processor, can send that transaction through the same network or scheme, but with different commercial setup, right? So for example, we can change the merchant category code that subtly alters your bank's kind of risk perception of that payment. So that's within acquire accounts within Adyen. The second lever is around smart payment messaging. So that's where we can modify the actual data payload, the ISO message that's sent to the issuer. Tweaking these configuration fields and flags to influence the bank's risk model and improve approval rates. We can do that without even changing the routing path. We can still have an impact on these approval rates. Every transaction is treated as a multi-arm bandit problem, where the optimization framework maps the transaction's context, the shopper, the amount, product, to the joint configuration of these kind of routing and messaging systems that alter and then maximize the approval reward. It's important to say, however, that optimizing approval alone is not sufficient. This is actually a multi-objective problem. As I mentioned before, there are these three main objectives from the merchant, but routing, introduces a structural trade-off, just routing itself, between authorization probability and scheme or interchange cost, right? Different rails lie on different points of the Pareto frontier. And a single global scalar weight between cost and approval doesn't actually generalize. So the optimal trade-off depends on transaction amount, merchant, vertical, issuer behavior, and retry stage. This routing policy that we have has to learn these context-dependent trade-offs dynamically. And so as we we scaled the system complexity, as I mentioned. Much of deep learning was kind of trying to learn these complex, higher order feature interactions between the issuer, the scheme, the merchant amount, and sort of moving between the flags themselves, reward function, relationship learning, and then use residual connections to retain original feature data. The next step here that we had to solve was unconstrained self-attention becomes unstable in production. And that led us to exploring late attention to improve that stability. So late attention has effectively changed the architecture because the raw data tokens in tabular data were too unstable, as I mentioned. So this new structure of late attention was a little bit better because it forced the model to first create intermediate combined features or cross representations before running the attention mechanism. This made the model really stable and robust using just plain self-attention. But still, late attention had a major flaw. And that was around temporal leakage. It was basically accidentally our model looking into the future. And so we started to look into causal attention to fix that leakage issue and also continue our path of trying to constrain the features that the bandit was thinking through. Payments data has a strict temporal structure, right? So some signals are available just at the moment we take a decision, things like bin, merchant, amount, historical embeddings, but other signals are just revealed to us after we take the decision on what action we take. So issuer responses, retry outcomes, chargebacks, downstream friction. And if these post-decision signals leak into training, the model can exploit correlations that disappear once you intervene. So offline it looks great, but online it collapses. So standard global self-attention allows every feature to attend to fine-tune it for diverse objectives. So if you're the fraud team, you can use this foundation model for that was lost from a foundational backbone. Patterns. And so our bottleneck at Adyen shifted from exploration and reward modeling that I just talked about to representation learning, which motivated the need for a foundational model. The vision for Adyen's foundational model is that it will power all of our tasks through a rich shared feature backbone. At pre-training, a large-scale transformer encoder, Adyen's entire transaction graph to learn that kind of backbone. So instead of having different teams within Adyen trying to handcraft their own features, effectively losing a lot of information by splitting these different data sets apart, we have a foundational model that kind of puts it into one shared encoder, which all of the different teams can have access to. It collapses and brings all of the context that was lost from splitting it back, every team can kind of access this foundation model to perform the task that it needs to do, right? Whether you're doing and you can adapt. The idea is that we rapid adaptation. So you can add a simple. Every team can add a simple lightweight head layer to the shared backbone and quickly fine tune it for diverse objectives. So if you're the front and you the optimal representation for payments. A payment transaction is fundamentally distinct from text or images. It's complex structured tabular data categorized by high cardinality categorical data. So that's like merchant ID, bin number, issuer. We've got numerical signals, so like transaction amount, transaction velocity, recency. We've got temporal structure, so we've got an inherent time series component for payments, right? We've got also even sensitive data like PII. And so we drove our strong temporal dynamics. And so it's important to think about two things. One of them is structured encoding. So you need to capture the data's inherent organization. And then you also have to think about sequence modeling, right? So you need to think about, leveraging the inherent temporal dependencies within payment trajectories. Our goal was basically first to start modeling what an individual payment is, right? And do this via an encoder-based approach, build this foundational encoder for payments. We want to treat effectively a transaction as a sentence and these fields as tokens and learn these contextual embeddings through self-supervision. The initial model that we built was Payment BERT, right? It's a tabular version of BERT that initially focused on individual payments and no sequences. The input features like bin, merchant ID, amount, treated like words. And categorical features used embeddings, and these numerical features use projections. And so our goal was to produce this dense. We realized that the critical unlock was modeling the history, the full sequence of transactions for an entity to predict things like risk. This led to like a radical shift. We saw the full sequence of transactions for an entity to predict things like risk. This led to like a radical shift. We started treating the entire payment or sequence of payments not as a collection of numerical or categorical features, but as a single long piece of text. To do this, we serialized the payments into structured token sequences. Effectively, has very high context window inefficiency perspectives, right? The shopper, the card, the merchant, or the broader market. The power of our system is in its single shared backbone encoder. This encoder is trained to simultaneously compute the authorization interacted buyers that we built. In 2026, we're going to be looking very deeply at thinking through a hierarchical foundational model. So the key thing is we want to build encoders for merchant sequences, and all of these act as like Bayesian priors, right? We then want to think about hierarchical fusion. So how do we combine all of these summary embeddings, transaction, shopper, card, merchant, and market, and fuse them together using a small attention block to produce this final universal representation? The pros of this approach is interpretability, right? We have embeddings for different levels of the hierarchy of a payment. We also have context window efficiency, so we use summaries rather than the full sequence that I mentioned. We also deploy this domain knowledge prior. So explicitly modeling hierarchy is a really strong prior for payments. The negative, the primary objective is mass language modeling. I'm going to talk a little bit about these two different joint objectives, can lead transaction level payment transformers and payment BERT. 2025, we focused on text-based sequence modeling and the idea of multi-view embeddings in the beginning of that journey. And this year, we're really focusing on hierarchical sequence modeling for our foundation model. Each iteration that we've had removed a bottleneck and exposed these deeper representation challenges that we've been trying to solve. I'm going to talk a little bit about pre-training this foundation model. Our foundation model uses an encoder-only architecture and is trained using self-supervision, right? So we don't really need initial labels. The primary objective is mass language modeling applied across billions of transactions, very common for foundation models. The core idea is to effectively mask structured tokens within payment trajectories, specifically quantized numerical bins and categorical tokens, and then predict them from the surrounding context. This forces the model to learn the inherent structure of payments and how they work, encouraging strong contextual understanding and feature interaction learning as well. Beyond MLM, other self-supervised tasks were used to have been used in further enhanced representation learning, such as next event prediction. You've got a payment trajectory, you need to see what would happen next to that, or even to a shopper, right? You've got a set of shoppers, a shopper doing a sequence of payments, what would be their next payment? You've got contrastive learning to distinguish between same and different shoppers. So that's when we're trying to make these embeddings and encodings really, really powerful in splitting different shoppers apart. Cohort discrimination and temporal consistency as well. So after this extensive self-supervised pre-training, the model's embeddings are adapted, hopefully, and lightly fine-tuned for the downstream tasks like fraud, authorization, and chargeback prediction. We evaluate our embedding quality on clustering effectiveness, neighborhood consistency, and linear separability. And then for the downstream classification tasks, the key thing is we try to freeze these embeddings and train simple MLPs or logistic regressions to optimize for things like AUROC or log loss as well. So we can actually see how well do these embeddings actually use, how well do they actually work on downstream tasks, real downstream tasks of our teams. Do they actually improve performance? So the pre-training task is really, really complex. Our embeddings are trained on around 200 billion payments, which are
a little bit
in both for your attention. So now,
in physical and social science environments such as hospitals, and in the scenarios only
tested in our lab focus.
For every business need. Customer relation, right? It's to the plan, code generation layer, plan tree. The plan tree encodes the kind of operations and the order in which they need to be performed. It then undergoes a conversion process. We'll take a look at it in a minute why. And the converted plan is then fed to the code generation layer, which generates the binaries which are necessary for executing the query. The execution state and the data are fed to the GPU runtime through the executor. The GPU runtime then crunches the data and uses back the result, which is sent to the client. Plan conversion. So plan conversion allows us to make modifications
This is this very symmetric in one chip, and of course these data centers. I want to talk about is this move to requiring more of a guarantee. And this move is happening because an enormous amount of performance and optimization opportunities available if you can describe your work in this way. So what I have here is, a very figurative image of an inference workload. Typically, you think of this as a production and consumption style. You've got a prefill where you take in the query, you take it, and so on. And so at that picture on the left-hand side, the prefill is very compute bound. It takes an enormous, right? Its job is to manage what runs where and to do it dynamically. It's going to spin up these inference engines that are going to run prefill work, dedicating pieces, having separate processes, which is more about isolating different things and running them together on the GPU. So here you'll understand that the stream is the unit to which I submit to do the multiplexing. Stream B is living in box B, and my stream C is living in views, as well as different green content. And having a vocabulary, something up that thing. But that share with you the kind of ways that we're thinking about this is memory management. Memory management is obviously a system level thing. Memory management, where the orchestrator is managing everything. It looks all pretty here, but itself is local. The grid is local, and the graph covers the entire system. And that's a key decision point for us. Core pieces of this is called the flash infer. NSight has cloud development tools for managing this kind of thing as well. There's something called cuFile as the API for that, and it allows Dynamo to be very specific and detailed in how it controls where the different KV cache locations are stored. And it also allows for low latency transfers directly between the GPU and the storage. We've also got a checkpointing mechanism. This is one of those really interesting things. When you build something in engineering and people use it in ways you didn't expect, it's always fascinating. And here it turned out that checkpointing, there's this great talk by Modal, which I've referenced at the bottom. I link talks at the bottom of these slides, by the way, relating to any of the things that I'm talking about. And the idea of using it for elasticity instead of resiliency was a really interesting thing that turned up. And it turned out to be a very powerful thing to do. And finally, of course, developer tools for this. We have to be able to investigate and inspect what's going on. And so NSight has cloud development tools for managing this, very powerful. And I'm going to look back at Dynamo and disaggregated inference, that the performance, and what we did, which picks a different tile size. Blackwell's a bigger machine. Changed, the kernels just moved from GPU to GPU with building ability things I was telling you about with tile. You can pick whatever thing you want, but you should pick the best one because it makes your life. If you're sophisticated enough or you want to put the time in, it turns out that some of the kernels are much more of a win than others. And so you can mix and match what it will, and while looking C++-ish, you still have the same language and the same similar, intentionally. It comes through NVCC, which is our C++ compiler, but we've made sure that the C++ sort of idioms, while looking C++-ish, you still have the same language and the same the same look and feel between Python and C++. I strongly believe your intuition should just map implementing this algorithm, and we ran it on a test. We wrote a kernel implementing this algorithm, and we ran it on a compiler. When your problem can be mapped onto it, the compiler can do so much more for you.
Manager, and also Oleg Sudakov, a senior solution architect. Today, we'd like to talk about how to teach an AI to code in every language. And that means to do not only focus on English, but also covering other human languages, such as Spanish, for instance, to focus on not only Python, but other programming languages, in this case, Rust. We will start by explaining the very basics of an LLM, how it works, and how we can use them for code generation. Then we will explain the results of our experiment. We train a code model from scratch, and we would like to share with you our lesson learned. Then we will focus on the different steps of that experiment. We'll explain how to do data preprocessing, how to do pre-training, how to do post-training, and which tools we use for that. Finally, we'll explain some applications that we can do with LLMs, and we will cover some specific focus like speculative decoding and a few other things. So let's crack on. Let's start by explaining how an LLM works. Most of the LLMs we use today use what we call an autoregressive loop. What's that? We have the user input that we call it prompt. For instance, the user input can be a question, or it can be just a sentence, such as the cat sat on the. And the LLM, which is represented here in green, what it will try to do is to generate the next token, okay, the most likely token after this sentence. A token is not exactly, it's not a word, okay, but we will explain that later. For now, let's assume that a token is a word, even if we are aware that that's not correct, okay? So for the sentence, the cat sat on the LLM might produce maybe the word mat. The cat sat on the mat. And then we will feed this word back to the input, and we'll try to generate the next most likely word or token. In this case, could be the cat sat on the mat, and maybe it's with his friends, whatever. And we keep on generating one word, one token after the other until the LLM considers that it has nothing else to add, or until we reach the maximum content length, which is basically the maximum number of tokens that the LLM is supposed to generate. Let's continue with our previous example. In the previous example, we were trying to generate the next word of a sentence. If you recall, it was the cat sat on the mat, okay? In this case, our input, our prompt will be slightly different. It will be write an efficient Python function to check if the number is both prime and divisible by 5.
Or overall usefulness of a document or a paragraph. We also can apply some bad Unicode characters, broken new lines, or repetitive text, for example, that can appear very often on web data sets. The second thing that we can do is document level filtering. Here we remove low quality content using several approaches, such as like a classifier-based quality filtering scoring, where we evaluate things like accuracy, clarity, coherence, grammar, or overall usefulness of a document or a paragraph. We also can apply some heuristic filters to catch any obvious issues. And finally, we can perform some data classification to remove, let's say, personal information, or classifiers to detect domain, toxicity level, or complexity of some of the documents. Several deduplication techniques can be applied, from lexical deduplication, including exact deduplication or fuzzy deduplication, which consists in identifying documents that are not exactly the same but very similar. Techniques can be used like min hash, for example, for that. We can perform also semantic-based deduplication, where we use some sort of embedding.
Good afternoon, everybody. Welcome to GTC. Hopefully, you are enjoying it. And first of all, I want to say, throughout the drive, you'll see, walk you through what we have been doing. All right. To kick off the presentation, actually, I would like to first show a video, which is what my team did recently.
In our cars. Throughout the drive, you'll see the car is constantly evaluating its surroundings in real time. You can also ask the car for information about your surroundings. Hey,
There's a vehicle crossing my path ahead. I'm going to yield.
what sets Alfa Romeo apart is how it... Hey, Mercedes, pull over here.
Sure, I'll find a safe place to drop you off.
Alrighty, hopefully this video, thank you. I think my team does deserve a round of applause because they have been working super hard with these keynotes, physical AI. Every year, across all different segments, roughly speaking, there's 13 trillion miles being driven by a car or a delivery motorcycle, a delivery car, and obviously there's other use case as well. And as of today, only 0.006% of the mileage are driven, a slightly different form. So as Jensen mentioned, physical AI problem is a three-computer problem. So in Drive AV, in NVIDIA Drive, we have really three computers, the training computer and the simulation computer in the cloud, and the inference computer in the car. And we are going to build 5 layers of services on these three computers. Guardrail for, last but not least, infrastructure. And at the core of it, and on top of that, we're also working with our partner, AI supercomputer. It's based on the Blackwell architecture, FP4. That's really basically 20. On the left side is our base model, and this is obviously more focused on the cost, saving in terms of at the BOM level. But Halos, as I said, is a unified software safety foundation for include TensorRT and LLM SDK, so that we can enable the software is generalizable across different OEMs. But from the safety foundation, over the last 2 months, it was actually number 2 in the most downloaded application or model in the whole robotic space on Hugging Face. It was downloaded more than 160,000 times. I didn't even know there's so many people working on AV. But we are very happy about what we the result. And in AlphaMayo 1.5, it's still a 10 billion parameter model, but we are going to make it more powerful. So what are the changes? Number 1, we are going to introduce routing capability into the model in different formats. It can be waypoints, or it can be nav guidance from a let's say a navigation software, or in other let's say vectorized format. Ask what the car is trying to do. The industry, the Cosmos Reason model, which was obviously part of the Cosmos Open model family, and Cosmos, the foundation model, was trained with internet scale data with 20 million hours of real world data. And then on top of that, there's basically Cosmos predict, transfer, and then. However, and this is a typical pipeline, which is what we use for internal effort as well, which I'm going to show in a later slide regarding how to fine-tune the AlphaMayo model and get it ready for production. So you would need lots of data set, obviously, either through data collection or through synthetic data, which Cosmos can actually help over there as well, which is also open failure mode from the to help, again, the ecosystem to be able to train the model. So we're not only open source the model, it's collected into like soon, not yet, but develop our stack. So field and save it for other use. And then basically you can also change, modify the obviously trajectory when this kind of object shows up, and then feedback. Can we go back to the previous slide, please? Yeah. So the basically then feedback essentially to insert and deploy to the car. And the other one, which is extremely important and extremely powerful, is Cosmos Transfer. Again, Cosmos Transfer, as I showed you guys briefly in the data pyramid, is a part of the basically a Cosmos family, enabled the first version of Autopilot. And the next generation, basically Xavier and Orin, they really started the massive transform or bring up of AV technology in China and the rest of the world. And right now, basically, at least in the China market, you cannot really sell a new car, without a good AV capability in it. And we announced, as I said, we deployed our technology to human-like driver experience, and meanwhile without compromising basically the safety interoperability. So this slightly busy diagram shows our stack. What's important here is that AlphaMayo, which is the production version of AlphaMayo, is our end-to-end model running the stack. By the way, we're running everything here in one Orin. And basically, this is a LiDAR-less and a map-less stack. And on the right side, it's our classical stack. And on top of that, basically, we have a safety arbitrator, which can guarantee safety when the stack is. As I mentioned, take it on the side to maintain safety. And another important point to hit is basically our current software structure is actually very much scalable, or extendable to L4. So this slide shows what is also have the try to scale L2++, from address to address. And starting from next year, we want to start the initial deployment of our L4 fleet. And by the in 2028, we will basically deploy L4, in passenger vehicles with our partners. All of the top 10. We are also basically really need everybody to work together, and we are very happy to work with everybody in the automotive basically industry, including OEMs, tier ones, or AV software development, to work with everybody in the automotive automotive basically industry, including OEM, talked about today. Again, Driver AV is walking for to the next step, which is really basically this year is about scaling of L2++.
Hello. Hi, everyone. Welcome to our very exciting session. It's titled Beyond the Black Box, Interpretability of LLMs in Finance. And my name is Ari Shader, and we are a team of AI quants that focus on AI applications across all of Barclays, including risk finance and trading. And we're going to talk about a very important topic that we've written a paper about that really focuses on understanding how LLMs work. And I'll hand it over to Hariam to introduce himself and kick it off.
Thank you, Ari. Hi, everyone. My name is Hariam. I work with Ari in the team called Risk AI ML. We work on several use cases of AI and Gen AI. And just continuing to what Ari mentioned, for this paper, we used a lot of resources from the researchers, from OpenAI, DeepMind, Anthropic, their papers, their code, and we gave a tweak for those research and gave a finance angle to that. And that's
the right features to answer that
as well. We try to have richer the encoder
data flow word activated a class
make the model obsessive, which was at
risk.
All the information tool we use here in two features, which then we had features which add information
data set of the
model. Side is the result of very important thing to note here is that the
application we tried of the credit sentiment steering is we have real application that actually classifies sentiment that comes from the news. And there's always some sort of accuracy problems. So what we tried is the following. We have a pre-labeled
LLM might have or well-adopted use case. Warren Buffett AI.
Wrap up this, this use case and move to exciting Warren Buffett AI. Ari will talk about.
Yeah, thanks, Ari. Yeah, Warren Buffett AI. You guys might have guessed this is related to trading, which is one of the most common, very famous, or well-adopted use case. Now, one of the main argument here is, just taking a step back, is that the brain of LLM already has all information on the entire internet, right? So all these models and approaches and the factors, features, all these trading firms use, LLM might have it already, and it's because it's trained on the history of the stock market. It's trained on things like pricing anomalies. It might already consist of things like, let's say, subprime crisis related information or COVID related information. Micro regime signal, when we see regime shift, that might already be baked into LLMs. Volatility shift pattern might also be baked into LLMs, and even the satellite image information. It's a weird thing we're trying to do here. And that's what we use to get the relevant features from this sparse autoencoder. We talked about how to get on the top. So what we are doing here is we had some news headlines, last 10 years of news data, multiple of news headlines, more than 10,000. That's what we use to get the relevant features from the sparse autoencoder. We talked about how to get the relevant features in the previous use case. Here, what we are trying to do is trying to get the relevant features for response to the price going up. So what we are doing there is for getting the features, we run it by multiple news headlines, as I mentioned in the previous slide, close to 10,000, and we try to see what are the features which are activating quite a lot. And generally, we try to capture the features which are related to finance or the financial features. Now, this is just an illustrative example. Something the folks in finance, they would know. There's something called named entity recognition, which is being used in a lot of application, a lot of use cases. That interestingly came out to be the most relevant feature. And the next one was financial terms, again, really important. Then we had stock ticker symbols and finance related abbreviations, again, which is important. And most of these features were really, really relevant. You will see it's not a surprise, even while we train some of the trading models, we see some of the spurious correlation, and that's what we see here as well, car and vehicle related terms. But keeping that on the side, this is really relevant. And the results were very, very intuitive, especially the first one, which was named entity recognition, or the NER feature. So really great outcome of this. And we'll talk about how we're expanding it even more in the subsequent sections. So next use case is hallucination police. This is something which is not just limited to finance. It can also be used for other domains. We try to do the references, use better model reasoning models and whatnot, human in the loop as well. All these are good, but what we have done here is, again, like the previous use cases, we have looked inside the brain of LLMs to find out the hallucination, or to kind of figure out or reduce the hallucination. So the activation features. So we had bunch of financial sentences and financial phrases. We try to find out what will be the features related to finance. Once, let's say, we found out 20 to 30 features, here is a crude threshold, the right and ground to choose which one might be activated. Of course, activation is one of the main thing, but you can also look at the feature label. And that's why we looked at the first one, which is related to finance, 5405 as well related to finance. And then there are a bunch of other ones, 15354, for example, it's again related to financial news and companies. So this is how we pick the features. The result, how does the result look like? Now, we asked it a question, for example, related to the timelines around regulatory filing for 8K. Right? So the left-hand side, when there is no conditional check, you just get the business days. It also paper. And even fine-tuning or training the toolkit ourselves. So one of the use cases is what we are trying is augmenting classical factors. So this is kind of extension of what we talked about in the previous slide, which was related to Warren Buffett AI. So in finance, we have been using classical factors for our trading models and factor modeling. Some of the classical factors we use are on the bottom left-hand side. For example, we have been using S&P 500, return of the stocks, volatility, the historical data of the stock, even the news sentiment. Now, the point here is, why not we augment those with the features we get from LLMs? So some of the features, for example, on the right-hand side, if you see insider buying, that's one feature in
a reasoning fault. We're using this, and we use an interesting, going down the software stack. We use NVIDIA, so you don't have the hardware. You can always ask your favorite vendor working to
in finance and also high stakes domain. Why? Because going back to some of the slides that I talked about,
the most and right now, how we are organized our AI Center of Excellence in order to see how
computing and
technology is a new
we approached the journey
allocation, reactive scheduling, and multi-objective
現在ですね、日本では、を活用して数を増やせば、よりそういうそうな質問を生成したり、例えば若年層もすごい LLM 使ってるんで、SNS のトラブルだったり、バイトテロっていうのをテーマに実際に起こりそうな質問を生成したり、会社員、ものによっては有効を作るケースももちろん弊社あります。で、その場合にも多くの課題が存在。例えば今、なので本当狙いとしてはやっぱり、本当今って量もすごく大事だとは思うんですけれども、本当にモデルにとって有益な質の高いデータだけを抽出していきたいなというのが背景としてあります。で、ちょっと下に、
壁があるというふうに見ております。一つ目は、NVIDIA さんの孤立されてしまっているのが現状をどうやって保護するんですかとか、実現しております。実際にこの経で今、実際にロボットが動いている空間の中に人が入って、その人がどういうことをしそうかということを今、一般人が人に入って、エリアに入ってきました。でそうすると、このロボットがそれを認識してパトロールを行います。で、今、画面の方にですね、ステージを歩いているとか、ロボットを眺めているとか、プロジェクションに見入っているとかいったものが見えておりますが、これはカメラから撮影した映像で、先ほどの人が何をしようとしたか予測しているものになります。そして何かですね、ちょっと不審な方が入ってきたというところを検知すると、それ先読みしてですね、空間の雰囲気が変化します。そしてこのロボットが今、いわゆるパトロールモードからですね、警戒モードに切り替わります。で、実際にこの警戒をするんですけれども、この人が立ち去ると元のパトロール状態に戻るというように空間の雰囲気を認知するということを実現しております。で、入ってくる人がですね、別に怪しい行動をしてなければ、警戒状態にならず、パトロールを続けるといったところで、きちんとそこの認識をするということが一つのポイントになっております。それでは次に、NVIDIA の VSS と弊社の
Hi everybody, my name is Christopher Payne. I'm from Imperial College and I'm delighted to present to NVidia GTC. And that could potentially, mostly going to show you are based on integrate with data assimilation, digital twins and uncertainty quantification and the methods that I'm mostly going to show you are based on convolutional neural networks. So we use convolutional neural networks to where we have a filter, for example, a little 3x3 filter shown here in this example, where we pass that filter over a feature map, and that could potentially take a transient problem from time step n to time step n+1 with a linear activation function, for example. So an example of the sort of filter that you could use is shown bottom right, where we show the sort of filter that you would use to solve Laplace's equation, let's say. You can repurpose autoencoders to form multi-grid methods using this kind of approach, using convolutional neural networks. And we're looking at the top here, we can see a restriction through a number of increasingly coarse grids. In a bit more detail, you can see at the top of the page, the top bottom right, you can see how you can use a neural network, or in this case, a UNet, and repurpose it to produce a multi-grid method. So we're going to be doing that within the neural physics approaches. And in the case of solving the Navier-Stokes equations, we solve the bottom, the pressure equation, using a projection method, multi-grid method, which is essentially a sawtooth multi-grid method. So it's one of the simplest multi-grid methods. So if you do that, in the next slide, we can see an example of what that workflow can do. So here we're modeling flow over the South Kensington area within London, and the geometry is shown on the left and the flows are shown on the right. So here we're looking at the flow at the speed of the air at 5 meters above the ground level, and you can, if you look carefully, you can see that we're capturing the transient turbulent motions, not just how they can interact information around out of the so that's important for things like light or filters to nuclear reactor. The bottom, so it's a three-dimensional model in this case, and we're looking at the scalar flux distributions of a number of energy groups, bottom right. So those energy groups represent the speed of the neutrons. So that was all convolutional neural networks with structure in the grids. On the next slide, we show the application of the neural physics approach to using graph neural networks to solve simple benchmark problems. So it's flow over the cavity and flow past the cylinder. And you can see it does quite well. But it's a general concept. So within the next little section, I'm going to hopefully show you that you can resolve a whole range of problems. Next slide, where we'll show you the results of that people from that information city through the detailed models that we've produced, interacting with or assimilating the data from, for example, open weather, obtaining very detailed distributions of pollution, temperature across in the summer, an app called BreathBot, which collects information from smartwatches and produces AI breathing rate over time for an individual within more pollution. So this particular individual, so we've doubled the exposure of that individual to the pollution that they were exposed to within over a few days. Pollution, the libraries that have been generated for quantum convolutional neural networks.
All right, have a great GTC!